Okay, so last day we started talking about Poisson process. I mean, we started talking about stochastic processes. And we divided it into two categories. One is arrival type process, and we had another process which is Markov process. But we said this is not a part of the syllabus, so then we talked about arrival type, and we particularly talked about two different kinds of stochastic processes. One is Bernoulli process, another one is Poisson. In fact, we said that this Poisson process, okay, so this is an extension of the Bernoulli process. In fact, this is a continuous analog or continuous time analog.
Sir,
Yes.
sir, tomorrow is test or not, sir?
Yeah, I'll talk about it tomorrow. There is no test. I'll talk about maybe a little later when some more people join. Then I'll talk about it. Okay. And if I don't, just give me a reminder. Okay. So I'll finish
Okay.
by Poisson process and then I'll talk about the exam.
Okay.
Yeah. Yeah. But yeah, tomorrow there is no exam because tomorrow there is what is called this convocation. Okay.
Convocation.
Yeah. Convocation ceremony is there. So there will be no class. That's what office order is. Yeah. Obviously there is no exam. Okay. So continuous time analog of the Bernoulli process. Bernoulli process is actually the Poisson process. And we picked up a typical example when we are discussing Poisson process. We said, okay, let us just consider, I mean, when we are transforming this time from discrete to continuous, I said that, okay, so there is a purpose of doing it, okay? So we considered a model and we said, okay, let's say it is kind of like traffic accidents in a city, let's say, in a city. So here success means there is an accident. Also, I should not success, but a failure, let's say, whatever it is, okay? So since this is in terms of success and failure, so let me say success means, okay, let's say at least one traffic accident, okay. And let's say in a minute kind of a thing, okay, in 1 minute period, let's say in a minute. So my observation here is per minute. So if you remember the Bernoulli trial or this binomial distribution, what you had is, so if this represents the time, so you are just tossing the coin. So let's say the time gap is 1 minute. So same thing is here. So if you observe, okay, accidents, okay, in a city, traffic accident in a city, so it could be either success, okay, or it could be failure, okay. So this is what is the Bernoulli process, okay. So it could be failure, success, failure, whatever. It goes on like this. So this is list. If I start right now, so this is my first observation. Then after 1 minute, I have the second observation, third observation, and I keep on doing that. Let's say, okay. But and here, then we also assume that, okay. So we also assume here the basic assumption. Our basic assumption was that the traffic intensity, let's say, is constant. Intensity is constant. okay, over time, let's say. And what it means is basically that the probability of an accident, okay, should be the same during each period of time, okay, over time. Okay, and not only that, we another assumption was that this success, let's say, okay, this is independent of whether success happened previously. Okay, so all these time periods, let's say, in each 2 minute, each 1 minute, let's say, this happening of this thing, the accident. Okay, so the events, let's say, or the possible outcomes, let's say, okay, at different time periods, they're all independent. Okay, so independent trials, independent successes are independent, something like that. And let's say what time and successes are independent. Successes are independent. Okay, and then of course we have a Bernoulli process, but the drawback of this model is that, okay, so in a minute, okay, there can be more than one accident. So this Bernoulli process, okay, cannot address that issue, for example. Okay, so it cannot track, okay, it cannot keep a track of the exact number of accidents, let's say. Okay, it only fits into the model when there is an accident or not. And then you say, okay, so if I want to extend this model, the question will be, okay, so okay, at the same instant of time, maybe there can be multiple accidents, or maybe in between the gap, okay, there can be multiple accidents. But if I want to measure this precisely, okay, what is happening, then we can discretize this time a little bit more. Let's say here it was 1, here it was 2, here it was 3, and then we can introduce some more observations here. Okay, some more observations here. So once I do that, then, okay, so some more observations here. So this is 1, this is 2, this is 3. And let's say instead of doing it per minute, we can talk about per second. Even we can go further, we can talk about millisecond or nanosecond, whatever my measure is, okay, whatever my number of observation is, okay, during the time span. So if I keep on reducing the gap of my gap means the time in between the measurement, okay, then this time, okay, this time axis, okay, this will all automatically, okay, be continuous. And here you see, for example, let's say here it was failure, success, failure, and if you observe the real situation, what will happen is per minute or per millisecond or per second, there the probability of happening of an accident, okay, will go very less. Okay, it will be very small. Okay, so what is happening is, instead of considering the time as discrete, we can consider the time as, let's say, as a continuous time, and then we can talk about intervals. Okay, what is happening, the number of accidents in an interval. Okay, we can divide entire time into set of intervals, and we can talk about that. Okay, so this is what is called the continuous time model. So when we say that we increase the value of a number of, when we increase, okay, so increase the number of observations, okay, observations, and of course simultaneously p goes to 0. This n and p, okay, observations n, let's say. So n and p, they're nothing but the parameters in our binomial distribution. Okay, n is the number of observations, let's say, and p is the probability of occurrence of that. Okay, so yeah, so once we so what I'm doing here is, now say when you talked about stochastic process of like arrival type process, so here it is like arrival here means that arrival of that accident, traffic accident. Okay, so once you do that, so then what happens is, instead of discrete domain, time domain, I have now continuous time domain, and n is increased and p is simultaneously 0. And then we said, okay, so if we consider, and so because n is increasing, p is going to 0, p is decreasing. So if I have an assumption, or if I have faced this kind of situation that np is almost a constant, okay, if it's like a constant value, okay, we increase n, decrease p in such a way that it is constant, and then we can consider this as a new parameter which can describe this continuous time model. Okay, from discrete to continuous. Okay, and we said yesterday, I mean last day, that then what happens is if we make this assumption that n times p is constant, okay, then mm, uh, this binomial expansion will automatically give you the our binomial, what is called the distribution, will automatically give you this Poisson distribution, okay, which we defined last day. So I said we'll prove it mathematically that how the Poisson distribution can be derived from this binomial distribution. So how this particular distribution, okay, can be derived from the binomial distribution, we will show it mathematically. Okay, when assuming that n is going to infinity, okay, number of assumptions, increase the number of assumptions, n is going to infinity, okay, n is going to infinity, p is going to 0, and this np is constant, and let us set that value to be equal to lambda. Okay, so lambda, we said it is like it can measure like a rate of arrival. That means here in this particular example, rate of kind of the occurrence of an accident, traffic accident. Okay, rate of arrival. So let us do that proof. Okay, so now remember that what we had, if we just recall the okay, so this binomial distribution. Okay, let's say k. I mean, I don't remember how did we denote it. Let's say k and p. This k success. Okay, and a number of observations with probability p. So it was defined in this way, nck. So it is factorial n by n minus k factorial, and then k factorial p to the power k, and then 1 minus p to the power n minus k. So if we expand this, okay, if we expand this, we have this factorial n minus n into n minus 1 dot 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 n minus k plus 1 divided by just factorial k, because the next term will be here in the numerator, the next term will be factorial n minus k. So it will get cancelled. It is this. Now since p here is lambda, here is np, so p we can write it as lambda by n. Obviously n is non-zero, so you can write that. So if we replace this p by lambda by n, so we have here lambda to the power k by n to the power k, and then 1 minus lambda by n, okay, to the power n minus k. So since here, now see here a k terms, okay, and here also we have k terms in the numerator, okay, here also k terms. So what we can do is we can, for each individual term from here, we can divide it by or multiply it by 1 by n. Okay, so then it will be n by n times n minus 1 by n times dot dot dot, then n minus k plus 1 by n. Okay, and then we can write this as lambda to the power k by factorial k, and of course the remaining term is 1 minus lambda by n to the power n minus k. Now say here k is fixed. Okay, so observe that k is fixed. K is a fixed integer. K is fixed. That's the first thing to observe. Okay, and n is increasing, so n is going to infinity. Okay, then what happens to all these terms? Okay, if n goes to infinity, okay, and then where does this go? So this will, anyway, it is 1, and this is 1 minus 1 by n. So meaning what? Where will this go? This will all go to 1, right?
1.
Yeah. So this entire thing, okay, will go to 1 because here, if we just write it down, so here it is automatically 1, and here it is 1 minus 1 by n, and here it is 1 minus k minus 1 by n. Okay, so all this term will go to 0, so everything will go to 1 because k is constant here. Okay. Okay, now next thing is 1 minus lambda by n. Okay, so there is one more term here, n minus k. Okay, here there is no term, n is involved. So here we have n minus k, so it can be written as the power n minus k is equal to 1 minus lambda by n to the power, let's say, minus k, and 1 minus lambda by n to the power n. Now, if n increases, okay, what this term will go? So if n increases, this lambda is again So it's a constant value. So it is kind of going to 1. And if it is 1 minus lambda by n, this is going to be e to the power minus lambda. This is math 1. So we'll not talk about that, how it is going to the minus lambda. You can also prove that. So it is going to the power lambda and everything else is going to 1. Okay. And except this term lambda to the power k by factorial k. So then what it means? So therefore we can say that this binomial distribution, when we have this k, n and p, okay, so or you can just write f of np. I don't remember what is the formula we had written. So this is, but k has to be there, number of success. So it is e to the power minus lambda and lambda to the power k by factorial k. Okay, so this is what we had actually, this Poisson distribution here. Okay, lambda to e to the power minus lambda, lambda to the power x, and this factorial x could be 0, 1, 2, so on. And the same thing because k could be equal to 0, 1, 2, so on. Okay, k equal to 0. Number of success means it could be 0, 1, 2, and so on. So that means in the continuous domain, okay, this is what we said actually before, that the Bernoulli process, okay, reduces to Poisson. Okay, so we can just repeat that thing, that Bernoulli process, or maybe we can just say that Poisson process. If I define it that way, Poisson distribution, okay, distribution can be approximated by binomial distribution. Okay, binomial distribution when n goes to infinity and p goes to 0. But so this is an asymptotic kind of a situation. N is going to infinity. Okay, so given a value of n and p, you can of course, given a value of n and p, you can of course consider what is the, okay, so let me write it down. So given, let's say, given n, p, and let's say k, okay, so then you can of course, given any value, so it is not infinity. So this is a theoretical limit. So this is the difference between calculus and other subjects in mathematics like algebra. Okay, here your limit means it's asymptotic behavior when it's n is going to infinity. But what happens to the problem in real life, n is never infinity. Okay, so this limit is obtained. Okay, this is a theoretical limit. So that means Poisson distribution, okay, Poisson distribution is a theoretical limit of, so when I'm saying that can be approximated when n goes to infinity. So that means what we essentially mean is in practical life that n is very, very large. Okay, and p is very, very close to 0. P is very, very small. It is never infinity. But theoretically, if you consider this to be infinity, then of course it is, this is the precise limit. So the Poisson is nothing but the binomial. But what happens in real life situation, n could be large, okay? But then the question is how much closely this binomial distribution approximate, okay, Poisson distribution if n is large. I mean, how much large it should be, okay? So I'm just, because if given n and p and k, okay, you can of course calculate this value because this is just a mathematical formula, right? So you can of course calculate this value, okay, whatever the way it is defined. And you can of course calculate also, let's say, f of lambda, if I write it, or f of lambda k. So this is for binomial and this is for Poisson, okay? So this is the Poisson distribution and this is the binomial distribution. Calculate the value. Then the question is, if I take how much large the value of n and how much small the value of p should be, so that this will match, okay? This will approximately equal to this, okay? So this is a practical question. So there is a rule of thumb, okay, that when it will be approximate. So okay, so there's a thumb rule, okay. It is like, so I would say e to the power minus lambda to the power k by factorial k. Okay. Last day we talked about the parameter as x. Here I'm writing success as k, so I'm writing k. Okay, but essentially they are the same thing. Okay, if I just write x in terms of x here, and we just replace x by k, so this is just a parameter. Okay, I'm using different notations because if you follow different books, so they also follow different notations. So anyway, it means the same thing if you understand the function. Okay. So yeah, so this will approximately be equal to this. Okay. So if Poisson, okay, our binomial approximate Poisson distribution, then it has to be approximately equal to this. Now the question is how much large should be, how much large the n should be, okay, or how much small the p should be, okay, such that this will be equal. Okay, so in computer, let's say when you do a simulation, okay, so a rule of thumb says if n is bigger equal to 100 and p is, let's say, less equal to 1 by 100, so let's say 0.01, okay, and let's say lambda is approximately equal to np, okay, then then binomial, okay, binomial closely approximates the Poisson. Now, so this is really an advantage. Why is that? You see, if you want to compute this value, it is a difficult job because if n increases, okay, so computing the factorial, okay, is a difficult job, okay. So yeah, so you have to compute this factorial of n, factorial of k, factorial n minus k. So this is difficult in computation. So but you can approximate it using this. So you can also say that using, I mean, in order to reduce the computations, okay, so Poisson distribution, okay, is useful. Okay, this is another way to look into the to discuss to explain the same thing. I mean, what is the use of Poisson? Let's say, so this is this could be another explanation. And if you compute the MGF, the moment generating function of Poisson distribution, let's say, I'll just define it. You can just calculate and find it. Moment generating function of. By the way, Poisson distribution is not continuous. So here, this k, the parameter, is actually k equal to 0 up to n, you see. So here I can say k equal to 0, 1 and dot dot dot, okay. So here also when you say it, so it is a discrete probability distribution, okay. It is a discrete probability distribution. Here you see 0, 1 and so on. But how it is obtained? By considering time as continuous. And you also said that when you explain a Bernoulli process, that this negative binomial is nothing but sum of uh, geometric distributions, okay, independent geometric distributions. So this was negative binomial yk, and this is sum of this. So here, I mean, during this process, like from discrete to continuous, you also have rediscovered a meaning of negative binomial. So what happens? Negative binomial distribution, it is nothing but sum of independent identical distributed random variable, and this identical distribution is nothing but geometrical distribution. So you can also explain that when you add random variables, okay, which are geometrically distributed and they are independent, then it will give you negative binomial. So this thing also is, so the distribution negative binomial distribution is also explained now as a sum of linearly independent geometric distributions. Okay, this is another thing which you discovered during this process from discrete to time, discrete to continuous time. Okay, so the MGF of Poisson, you can check that. So this will be like, okay, I don't know, let's say Z is the variable, or let's just Poisson. So this is here we used to write what is the random variable. So this will be equal to e to the power lambda and e to the power t minus 1. And we also said that if you take the derivative and all, you know how to compute moments from the MGF. So you can calculate that, and you can check that the mean for the Poisson distribution is this parameter lambda, and sigma square is also equal to lambda. So yeah, so now what we'll do is, I mean, I'll just, some echo is coming somewhere. Yeah, I think from somebody's microphone. Yeah, not from me. Okay, so I'll just give you a table to remember what is basically basic fundamental difference between Poisson and this Bernoulli. Okay, So I mean, you just remember the table, then it is enough to understand what is this. Okay, Bernoulli. So there are two things in mathematics. Okay, one is a formula, and another thing is there is a history. Okay, not a story, history. Okay, so there is a scientific evidence of that formula, like how it is based on, how it is derived, what is the use of it. Okay, maybe this is not very important. Okay, when you consider exam, because in exam formulas are maybe much more important about this. I mean, for exam in exam formulas are much more important. But if you want to develop a new concept, okay, suppose you have kind of a data and you want to, you find something, okay, so you observe something which is never observed before, let's say, okay, then you need to have an analytical mind, okay, so that's why, so this how this concept, okay, first time, okay, developed, first time was developed, so that is also very important. Okay, so this table I'm giving, it is not a purpose of exam maybe, but okay, so you can see that difference. Okay, you can remember like what is going on, what's the difference between Bernoulli and Poisson. So here, so both are arrival type stochastic process, and so times of arrival in Poisson, it is continuous. Okay, continuous, and here it is discrete. And if you consider the probability mass function of number of arrivals, uh, mm, PMF, probability mass function of number of arrivals. So this is what is called Poisson distribution. And this is what is called binomial. And if you consider the inter-arrival time, okay, or let's say waiting time. In some books they will write it waiting time, or waiting time. Well, that means this T1, T2, Tk, which we talked about. Okay, so this is I'm writing CDF. So this is because it was anyway. So this will be exponential here. Exponential, and I did not define what is exponential. We'll talk about it because it is a continuous random variable, and here it is geometric. Okay, so T1, T2, Tk, all these things are geometric. And arrival rate here is lambda per unit time, and here it is p, okay, per unit time. So this is the fundamental difference between Poisson and Bernoulli processes. Okay, now I'll conclude this discussion about Poisson distribution. Okay, with the definition of Poisson process. So we have now talked about, so we have developed the concept of Poisson distribution, and then how we formulate this idea into a stochastic process. Okay, how do we formulate this idea into the framework of a process? So here I'll just give you the definition. Everything we discussed, but let us formulate the definition. So definition of Poisson process. It is as follows. First, let me define a probability. Okay, so let me write it this way. Let P, so P some K tau, which is what? This is the probability of this. So that there are exactly K arrivals, okay, during an interval of length tau. So I'm dividing. So this time axis, okay, this time axis is divided into intervals, and The length of each of this interval is, let's say, tau. Okay. So this length is tau, this length is tau, this length is tau, this length is tau, and so on. So if that is a probability, and let's say lambda is a parameter, okay, now I am defining this Poisson process completely independently after developing the concept. This is lambda, let's say it measures, or it is called, let's say, the arrival rate, or you can also say intensity. Then we can have the definition. Okay, then the arrival process, let's say the arrival process, okay, is said to be a Poisson process with rate lambda if it follows the following properties. Okay, so the first condition is called time homogeneity. So time homogeneity, so which means the probability p k tau, okay, of k arrivals is same for all intervals, okay, of same length. Here it is tau. So meaning that you will observe k success in an interval of time, let's say tau, okay, is same. It doesn't matter on which let's say, yeah. So here it is tau. Let's say this is time interval, let's say t1, okay, but its length is tau, t2 and t3 and t4 and so on. So the probability that the occurrence of k traffic accident in this time span, okay, which has length, let's say tau, these are all tau, okay, they are all equally likely. This is what it means. Okay, this is the thing which we considered about Poisson distribution. Okay, second thing is it is independence. So these all are independence. Okay, so so the number of arrivals, MRF variables, okay, in an interval or in any interval, k is independent of the number of arrivals, okay, in other intervals. So it is independent of the history of arrivals over time, whatever history of arrivals, whatever number of accidents happening, doesn't matter. So in outside that interval, so everything is independent. Okay, is independent of the history of arrival. Okay, outside this interval. And most important, so these are we already said, and the most important thing about the Poisson process is what is called small interval probabilities. Small interval probabilities. So here the probabilities pk tau. So this is the probability that there will be k accidents, I mean the k arrivals, k number of arrivals, okay, and the interval length is tau, okay. They must satisfy the following. So p of 0 lambda, there is no accident during this, should be 1 minus lambda tau. So because lambda is the rate of accident, you remember order of this tau, because tau we can take very large, tau you can take very small. Okay, so it is kind of, I'm not going to the detail because this is kind of Taylor series approximation. Okay, you can assume like that. So it is coming from the Taylor series. So 1 tau, there will be one accident. It is approximately lambda times tau plus some order 1 of tau, and k tau, there will be k accidents, okay? It's of order k tau. I'll define what this order means, where k is equal to 2, 3, and so on. Okay, here, these are all functions of tau, okay? So these are all functions of tau. So here, or where order of tau and order of k tau are functions of tau that satisfy limit tau goes to 0, order of tau by tau is equal to 0, limit tau goes to 0, order of k tau by tau is equal to 0. What it means is, see the time interval, okay, on the time axis, okay, on the time axis, you can take a large interval, you can take a small interval, okay. But here what we are saying is how then the probability will change, but it will change up to certain extent, right? Because if you take a difference, if you vary your length, okay, of course this probability will change, okay. So what we are saying is this is the definition that if you take 0, okay, if you take number of success, that means number of traffic accident is 0. There is no traffic accident, okay, in an interval of length tau. So this is approximately 1 minus lambda tau plus order of this. So now we said that what is the meaning of this function order of tau? We said order of tau is going to be 0. So that means the ratio of this is going to 0. That means order of tau, if you consider this function, okay, this is negligible compared to this, okay, when the interval length, this tau is very, very small, okay. Similarly, order of tau square. So tau square means, okay, order of tau square, order of tau q, and so on. You can consider it like the terms in the Taylor series. In fact, you can explain, this can be explained much more deeply when you take a Taylor expansion of this probability value. Okay, so the thing is, the meaning of this function is that when you take small time interval, okay, then the probability of single arrival, okay, is roughly around this intensity times this tau, okay, plus a negligible term compared to tau. And okay, so it is, you can roughly say that 0 arrival is 1 minus lambda tau when order of tau is like very, very close to 0, you can say, corresponding to tau, and so on. I mean, the same thing. Okay, this is the meaning of, I mean, this mathematically, this can be explained as using these two conditions. Okay. Yeah, so this is what is called the Poisson process. We talked about Bernoulli process, and this is the Poisson process. When the time is continuous and the probability of k number of arrivals in a time span of length k, okay. So it does not matter when you measure during the day, whatever time you take, if it is a 1 hour or 1 minute or 1 second, this is the length of your time, okay. These are all independent of whatever happened outside this interval. This is the main important thing. Second thing, independence. And they are all equal. The probability of obtaining k success during morning or evening doesn't matter. It is all the same, okay. It doesn't depend on like which time during the day you are observing, you are measuring it, okay. So it is independent of that. And third thing is that if you make tau small, then there will be only a small change in the probabilities. This will also go to 0. So if you take time span is small, then it is going to be 0. Yeah, this is what it is. Okay, so this is where we end the discussion about Poisson process, and we go to the next topic. But before we go to the next topic, we need to talk about this exam. And let me tell you that the plan is that the exam, this class test, I mean the class test, okay, the class test, okay, this will be organized, I think, on Saturday, 7th. So March 7th, okay, Saturday. This is Saturday. Do you have any issue with that? This is proposed. March 7th. This is, yeah, March 7th, Saturday. A time is not decided yet. Hopefully it will be in the morning.
Sir, it's Sunday.
Sir, it's Sunday, sir. March 7th, it's Sunday.
Oh, March 7th is Sunday?
Yes, sir.
Then maybe it is March 6th. Okay, just, let me open my email. I forgot it. So just a minute. Where is that? Oh, okay. So, there is a new development here. There was an email in the morning today. Morning is just before 8. Okay. So, okay, it was supposed to be planned on 6th March, not 7th, by the way. Yeah, you're right. 6th, and the new development is, just before 8. Okay, so there is no announcement. That's a recent development. Who will announce it later? Okay, so we'll have to find a slot with a free slot with module people. Okay, and then it will be decided. So there is no exam tomorrow. That's the recent, very recent, updated information about class test, and it will be announced later on. Up to yesterday, so that was the date, March 6th, but now there is a new development. So there is no announcement about the classes right now. Only announcement is tomorrow there is no classes. Tomorrow means 23rd February, no class test. No class test. Okay, so this is the announcement. And when it will, when we'll be organizing this will be informed. Okay, you will be informed about that. Okay.
So syllabus remains same, right?
Yeah, syllabus is the same because question, we already have made the question paper, right? So the thing is, since tomorrow is a holiday, so yeah, we have to find a slot talking with after talking to this module people. Okay, because everything is online, right? Module people, okay, when they are available and other things. Okay, so yeah. Yeah, guys. So
But can it be in this week?
I don't think there is any chance. I would say, yeah, I don't think there is any chance because we have to inform you, right? So I don't think there is any chance that this will happen next week. This week. I don't think so. See, because the next week you have holidays, right? So from 26th, 27th, next Saturday onward, okay? 27th to 3rd, I think there is holidays. So there next Monday you have no class. Next week also you have no class, I think. 27th to 3rd of March. And 27th February to 3rd of March, spring break, right? So there is no class. So next week there will be no class. So before that, if you want to organize this, this has to happen before Friday. So I don't think it is going to happen because module people are not free. Okay, like you cannot say to module people like we have to organize the exam next day. It will not be possible for them because they have to do many things. And yeah, so I don't think it will happen this week. I don't think it will happen before the what I mean is before the spring break. Maybe it is after the spring break. And you'll be informed.
Sir, can you share the previous class test marks?
Oh, yeah. I think I can do that. Yeah, I forgot, I think. Yeah, I can do that possibly. So I'll ask the coordinator, okay? And I'll say, what
Sir,
happened in other
sections have
section?
already
Did they get
received
it?
their marks.
Did they get it in the
What?
other section? Did they get it in
Yes,
other
sir.
section?
Other sections got it long ago.
Oh, I see. Okay, then maybe I have missed somehow. Okay, maybe once I get it, once I get it, once I get the marks, I will upload it in this MS Team. Okay. The problem is
Sir, by
sometimes MS
when?
Team does not work. Yeah, by today or tomorrow. Okay. So the
Okay.
problem
Thank you.
is that sometimes it does not work. So like when I'm trying to upload, it does not work. I mean, I cannot upload it. So that's the problem. Or maybe I don't remember actually. Maybe I had tried sometime before. I don't remember. So I have to do that. Okay. Yeah, I'll do that. Okay. I'll keep a note of it. Yeah. Okay. Sorry guys. I actually maybe have forgotten. Okay. So now we turn into a new domain, which is like we'll start talking about now spatial distributions, okay, of continuous random variables. So we talked about spatial discrete distributions. I mean, discrete distributions meaning distributions of spatial type of discrete random variables. Now we'll talk about distributions, okay, a distribution function of spatial kind of continuous random variable, okay. Yeah, so this is what we have to do now. So, and the thing is here, you can observe, you can notice that we completely have forgotten about sample space. Okay, so meaning probability theory is not about actually a sample space. Okay, yeah, there is an underlying sample space. That's the basic assumption, but you don't care because as long as you find everything about a random variable or everything, you can find out whatever you need, for example, about the experiment, okay, which can be calculated through this probability mass function. So you're happy with it, okay? So we don't need to talk about sample space. What we need to talk about is how the PMF is defined. That means the probability mass function is defined. The same thing is also true when we talk about continuous random variable, okay? So now we'll talk about spatial or distributions, or let's say, yeah, the density function, okay? Density function, probability density function, let's say. Probability density functions. So it is now just algebra and analysis, a little bit of algebra and just analysis. You have to compute some limits. You are supplied with a function which is interpreted as probability density function, and you have to find out the mean, variance, Mgf, okay, course of the random variable, okay, whose density function is given by that function, okay. So probability density functions of spatial continuous random variable. Okay, what happens here is first in the beginning I mean guys, if you can you remember, right? So okay, let me just recall what was that. Probability of A is equal to X. So if the X is the random variable, it was defined by A to B, okay, fx dx, and this fx is actually the density function. So here, if you know this, that means if you know this function, if you know that this is the density function, some function is given to you, and this is the density function corresponding to a random variable x, then this formula is the formula to calculate probability of happening of x inside this interval A to B. So if this is the time or whatever it denotes, let's say it is the x-axis, this, and there is some kind of a function here, okay? And then everything is now in terms of area because this has the meaning of area. And if x, as we said before, this density function is always non-negative. So you'll always have the curve on the first quadrant, okay? And one of the properties of this density function was, the most important property is the area under this curve is 1. Okay, so the probability, okay, of occurrence of, let's say, in this entire non-zero, where it takes the non-zero values, let's say. Okay, so you can have this entire thing, and if this is the non-zero part, so that means that before that everywhere it is 0, before that everywhere it is 0, and yeah, so this area is 1. And if you give me some interval, let's say here is A, here is B, then of course there is C from which it is like this is the area. Okay, so A to B will nothing but, I mean, the probability of occurrence of X. So occurrence of X means X is, again, just to recall, X is a function, okay, from the sample space to R plus or non-negative numbers. Okay, so or just or it need not be non-negative. So S to R. Okay, now this S is uncountable. Okay, so this S can take any value from R. Here, sample points are not discrete. Okay, are not discrete points like 1, 2, 3, and so on. So it is like in a range of something uncountable, meaning it could be an interval or union of intervals or the entire R. So ultimately, whatever the sample space is, you are associating with real numbers. So this is where X is coming from. This X is taking the values of this random variable capital X. Okay, so this X is taking the values. So when I write this, so this means this is that event omega belongs to A such that X of omega is lying between A to B. So this, yeah, so this X is actually that number. Okay, the image which is in the image, okay, of this random variable X. Yeah, so this is what it is. Okay, now what we'll do is, if fx is of some particular kind, okay, some kind of a function, okay, which is defined in a certain way, then we have to find out the mean, variance, Mgf, and so on for that particular density function. Okay, and if it follows a particular, I mean, some special kind of a function, then we'll give it a name. Okay, that is the density function of, under that name, that is the density function of a random variable. Okay, continuous random variable. So the first example, okay, like we did it for the discrete, here is also the same thing. We have something called, this is the first one, which is uniform distribution. So in uniform distribution, so let me write in the beginning, let us write that, suppose or let me just write a random variable. Here random variable is continuous, so a continuous random variable, continuous random variable X, okay, has a uniform distribution, okay, if the corresponding fx is defined as follows. So this is defined as 1 by, let's say, b minus a for some a less than x less than b and 0 otherwise elsewhere. Now see, a and b are constant, okay, where a, b are real numbers, okay, real constant. So if you want to get a feeling of picture, okay, how does this look like? Okay, so then suppose somehow you have a, somehow, of course, a is less than b because of this condition. So yeah, a, b. So then what happens is the function, if you want to plot the function somewhere, whatever the axis is, doesn't matter. I mean, it does not mean that a, b are positive. Okay, so it is just the axis, y-axis. So it is something like that. And this value is 1 by b minus a. That means if it is here, fx is 0. If it is here, fx is 0. So elsewhere it is 0. Okay, and here the probability of occurrence, okay, is same. So if you can pick some particular interval here, and you have to just find the area, okay, under this. It is the area of this rectangle only. So this is how, so you can just join this and you can say like this is how it looks like. Okay. Yeah, so this is the uniform distribution, and You can calculate mu. Okay, what is the formula of mu? Mu is the expectation, right? Mu is the mean, the expectation, which is integration minus infinity to infinity. What is that? How it is defined?
X into f of x.
Okay, fx dx. So fx is known to you, okay? So you can just put in the value here and we'll see it is a plus b by 2. Similarly, you can find the variance. Okay, what is the definition of variance? What is the definition of variance?
X square f of x dx.
Okay, x square fx dx. So this is second order moment. Okay, so it will be okay. We had also seen like it is e of x square. Okay, minus I think e of x whole square. Okay, so anyway, if you do it for this one, I may be wrong with the formulas. Okay, you can just check it out. Okay, b minus a whole square that you can find. So if anything is known, that some you are given with some data points which follows uniform distribution. And this is the mean and this is the variance. And of course, you can also compute the Mgf. Yeah, and this is the first example. Second example, okay, now this is a
So
big
the
thing.
PDF is 1 by b minus a, right?
Yeah.
Okay, I thought that's heads.
Is that okay?
Yes, sir.
Yeah. So this value is decided by the interval. Okay. It is not any constant. This is decided by the interval a and b. Okay, so next example, and this is a very big example. It's a class of examples, you can say. Now we are interested in the PDFs, probability density functions, which are of the following type. I'll tell you what the following type means. So the function here is like that. Fx, of course, it is not a constant function like previous case. So it is some k, x2 we have some alpha minus 1, alpha could be anything. Okay, positive. Okay, I'll tell you what is alpha. X by beta when x is 0, bigger than 0, and otherwise it is 0. So now we are interested to discuss random variables whose density functions are of this kind. Okay, for some alpha, beta, and k. Okay, so here, okay, where alpha is this bigger than 0, beta is bigger than 0. But I don't know the values of k, but I need to find out because I know that if it is a density function, then I must have this property. Okay, fx dx, this should be equal to 1. So area under the curve has to be equal to 1. Okay, now so I have to find the values of k for which this is satisfied. Okay, so this is equal to 0, and we can find the value of k, such that this happens. So that it is a density function. Right now it is just a function. Okay, now it has to be a density function. Of course, it is non-negative. From the definition itself, we can say that k has to be positive, then only it is r bigger or equal to 0, then it is interest bigger than 0 because it is 0. Because the area, if it is k is 0, then everything will be 0, then it will not be density function because the area has to be 1. Okay, if such that this happens. So now we need to find out what is the value of k. Okay, such that this is equal to 1. Now say according to the definition, elsewhere meaning when x is less equal to 0. Okay, this is what it is. Now if I just write down that what is the value of this, okay, then what happens? I have to find the value of k such that this is equal to 1, fx dx. Okay, but this is equal to minus infinity to infinity k, and then x to the power alpha minus 1 e to the power minus x by beta, okay, fx dx, okay. So what we can do here possibly that we can first take the constant out, and we can also see here it is x by b. So let me replace that by any variable, okay. Let me say where, let me write it like y some into some new variable, y is equal to, let's say, x by beta. Then what happens? So it is well, so that is the case, then x equal to beta times y. Okay, so there are two constants I have to take out. Okay, so just a minute. So yeah, so this equals to, I'm not very good with calculations. Okay, so otherwise every time I'll do mistakes. So you have to take this k out and x to the power alpha minus beta, meaning y times, so beta to the power something, right? Okay, so beta to the power some, what will happen? Alpha minus 1. Okay, so then x equal to this is y, y to the power of minus 1, e to the power minus y. Now if you take dx, okay, oh, there will be one more beta here, so I have to just delete this, and then we have this dy. Okay, now this is, if you remember your math 2 or math 1 maybe, no, not math 1, I think math 2, there is something called a gamma function. You have studied gamma function?
Yes, sir.
Yeah, yeah. So since you know what is gamma function, let us, so I don't know what is, I mean, I do not know the value of this, by the way. I have to make this equal to 1. So for some value of k, it has to be equal to 1, okay? So I'm trying to now manipulate something, okay? So that, because I do not know how to compute this integral here, okay? So that's why I'm taking the help of gamma function, because it looks like a gamma function. Okay, now if we just recall what is that, so that's why, okay, I'll come to that. So gamma function, if you say recall, so it is gamma of alpha, this is 0 to infinity. Oh, by the way, I don't need to take minus infinity, I need to take 0 to infinity, because if it is less equal to 0, this value of fx is 0, okay, 0 to infinity. So 0 to infinity, I think is some, in fact, it is exactly the same thing. This is how it is defined, dy, and when alpha is bigger than 0, okay. And if you recall, and also this is how the gamma function is defined, and also recall the properties of the gamma function. In fact, gamma function is defined like this. This is a recurrence formula. This is alpha minus 1 times gamma of alpha minus 1. Okay, these are we just recalling from the calculus course. Okay, when alpha is bigger than 1. And if alpha equal to 1, what is that? Gamma of 1 is equal to what? So if you put alpha equal to 1, what happens from this definition? Okay. So gamma 1 is equal to 0 to infinity to the power minus y dy. What is this? What is this? This will be always equal to 1. Why is that? Because gamma of 1, use this formula. Gamma of 1 is what? Oh, but this is for alpha bigger than 1, right? So this is not for alpha equal to 1. So yeah, this is 1. Yeah. So how is this 1? E to the power minus 1 minus y, right? dy. You can do this integration, you can get the value, right? Okay. So this is another observation. And if you keep on repeating this, okay, here it can imply some nice formula if alpha is integer, positive integer. So we just keep on repeating this. So gamma of alpha is equal to alpha minus 1 times gamma of, let's say, alpha minus 1, and let's say alpha minus 1 is enough. I mean, alpha is bigger enough such that alpha minus 1 is also positive. So then you can apply it again. Minus 1 Okay, then alpha minus 2, gamma alpha minus 2, and keep on doing this. Okay, so then you can show that this is exactly equal to alpha minus 1 factorial. Okay, when alpha is, because I am just recalling this because we'll be using this. Alpha is a positive integer. Okay, otherwise, yeah, positive integer. Okay, this is another formula and another formula to recall. So this is another formula which I wanted to recall. And another formula, I think, if you recall this, gamma of half equal to square root of pi. This is another formula. And now I think we are ready, okay, to find out for what value of k, okay, this function is a density function. So for what value of k, this will be a density function. So this has to be equal to 1, right? So this is just recall, okay. Now I have to remember this. Okay, so this is just a recall. Then minus n to infinity fx dx. Okay, which was what? 0 to infinity some k beta to the power alpha. What is the power this? Yeah. So beta to the power alpha and x to the power alpha minus 1, right? And e to the power x minus beta. Okay, x to the power, what is that? Oh, e to the power minus x by beta. E to the power minus x by beta dx. Okay, then we put x equal to something, right? Y equal to x by beta. So we had k and something, right? Beta to the power alpha 0 to infinity. Okay, this was, yeah, 0 to infinity, and then what is that? Yeah, I think we had the gamma function here. So let me just write it down here. Yeah, so it is x to the power alpha minus 1 and e to the power minus y dy. So this is gamma function, where is gamma alpha. So k is equal, this k times beta to the power alpha times gamma alpha. Okay, now I want this to be equal to 1. Okay, this to be equal to 1. This to be equal to 1, which implies k is equal to 1 by beta to the power alpha gamma alpha. So for this value of k, this fx, which I originally introduced, okay, this function is a density function, okay, and this density function is called, for that value of k, the gamma distribution. Okay, so now we are ready to define a new continuous new density function, okay, for corresponding to a continuous random variable, which is gamma distribution. Gamma distribution. Okay, so same thing. Every time I'm not writing continuous because we are discussing continuous. So a random variable x is said to have gamma distribution. Gamma distribution if the corresponding function here. Okay, there are two parameters you can write sometimes like alpha comma beta, because these are the parameters how it is defined. Okay, so you can write it this way. So this is 1 by beta to the power alpha gamma alpha, this is k, and then it was x to the power alpha minus 1 e to the power minus x by beta when x is bigger than 0 and 0 otherwise, where alpha is bigger than 0, beta is bigger than 0. So this is a very, very special kind of distribution. Now there is a problem. Okay, problem is how do we find a value of gamma alpha for any positive value alpha. We said we can do that when it is a positive integers, okay? Like gamma of alpha is equal to factorial of alpha minus 1. But otherwise, how do I find it? So otherwise, how do I get the value of this, okay, this integration, okay? And this can be done numerically, and there is a table which is called the table for gamma distribution, where you will get the value of gamma of alpha for some specific values of alpha when alpha is positive, okay? Alpha is positive, very, very important. So yeah, so there is a table called, this is a distribution for the table for gamma values, or you can actually find, yeah, so the table for values of this function, okay, this can also be found. So I'll talk about the table, I'll show you the table maybe, okay. Once I discuss other other PDFs, other probability density functions for a continuous random variable. But okay, so but in any book you will find it, okay. So if you want to just imagine what kind of function it would be, of course it will depend on this value of alpha and beta, okay. You can take different instances of the pair of values of alpha and beta, and you can check out like what is happening, like what is the value, okay. So I can give you some instances. Well, how does it look like? So it will look like this. So okay, let me just label this 1, 2, 3, 4, 5, 6, and so on. Okay, this is my x and this is my fx, and this value, let's say 1. So if I take some alpha to be equal to half and beta to be equal to 1, then it will look like this. So it will look like this. So this curve, okay, is for alpha equal to half and beta equal to, this is a family of functions, right? So everything is clubbed together because it depends on the value of alpha and beta. And then again, you can increase the value of alpha and decrease the value of beta. You can take anything, but I'm just giving some instances, like how does it look like. So if you do that, okay, so it will be something like this. You get it like something like this. Okay, so like this. When this is for alpha is equal to 2, beta equal to half. And you can also something like this. So it is not taking a very, let's say, I would say, very particular shape, okay? Depending on different values of alpha and beta, okay, it will take different shape. It's like that when alpha equal to 11 and beta equal to 1/2. But at least you can see that the height is decreasing, okay, when I increase the value of alpha and decrease the value of beta. Okay, oh, this is not half, but this is 1/5. So yeah, so it will take different kinds of shapes. Okay, now if you a specific gamma distribution is called what is called exponential distribution, which I discussed when we talked about distribution, that is waiting time distribution or the interarrival time random variable. Okay, so that follows exponential. An exponential is actually a special gamma distribution. Okay, so this is my third example of spatial density function, setting alpha to be equal to 1 and beta to be equal to, okay, beta is, you can keep it beta, but standard practice is to just define this as theta. Beta is beta itself. Okay, if we just set alpha equal to 1, then what happens to the distribution here? Okay, then the gamma distribution is called the exponential. And from the name, it is clear why it is called exponential. Okay, here you can see, okay, anyway, so exponential distribution. So my definition is distribution. So the definition is a random variable. So this is the definition of exponential. A random variable x, okay, said to have a or or an exponential distribution, shear distribution, if fx, okay, here we are introducing the parameter symbol theta, but theta is same as beta in the earlier case. Okay, you can just keep it beta, no problem. So here I'll put alpha to be equal to 1 in this here in the here I'll put alpha to be equal to 1 and beta is of course theta, so that is not important. So if I put alpha equal to 1, of course I'll get 1 by beta one term and gamma of 1, so that's why I calculated gamma of 1. You see here gamma of 1 is equal to 1. Okay, here gamma of 1, this is a value of gamma. Gamma of 1 is equal to 1. So if I just plug in here gamma of this one equal to 1, and then x to the power alpha minus alpha is equal to 1. So 1 minus 1 0, x to the power 0, and of course e to the power x by beta the remaining. So I can just have this distribution. Okay, this sum 1 by theta. Okay, e to the power minus x by theta. Okay, when x is positive and 0 otherwise, and here where theta is of course bigger than 0. Okay, and from the name it is clear how should it look like, but let me just draw the picture. Okay, so this is my y-axis, let's say this is x-axis. Okay, and this is some value which is 1 by theta, and what happens is this distribution looks like this. Okay, it goes on. So this is what is the PDF. Okay, PDF of exponential. Now, because I said earlier that I'll show you that while this kind of, let's say, this exponential distribution can appear, we already discussed that when you consider Poisson distribution. Okay, so when I gave you the table here, we said interarrival time follows exponential when it is Poisson, and for the case of Bernoulli, it was just the geometrical distribution. You see, this was exponential. Interarrival waiting time or waiting time distribution, okay, is exponential for Poisson. Okay, so yeah, we can prove that. So yeah, so we can prove that means we can again explain everything, whatever the Poisson process. I can do that, but if I want to do it, I want to make it very, very simple. So let me do it this way. Let me explain how this exponential is coming up when you talk about this interarrival, okay, time. Okay, the random variable corresponding to interarrival time. So suppose, okay, suppose okay, the probability of getting k success or maybe x successes, okay, during a time interval of length t. Okay, so it is same thing as saying the previous thing. You can remember k comma tau. Same thing I'm explaining, just placing the symbol x equal to k and t equal to tau. Okay, because in different books you will have different notation, but it is the same thing. Okay, this is what it is. Okay, probability of this in the previous during the discussion of Poisson. And then we had some assumption, right? Because this will be the probability, and this probability will have to satisfy, okay, those three conditions of Poisson process. So what are the first condition? First condition was the probability, okay, of success. I'm just rephrasing this. I'm just recalling this. In a small time. Now time here, that's why I'm writing a t. So time, let's say probability of success in a small time interval. Let's say, let me now write it as t and t plus some delta t. Sometimes we'll write in physics, you'll see, or in other literature also you'll see, we if we have a small change, we'll write it as delta or delta t. Delta t means it's the same number. Okay, it's not delta times t. So it is just very small perturbation of this. Okay, so suppose the probability of success in a suppose a small term this. So I'm measuring the probability of success as this alpha times delta t. Now see, alpha is playing a role. If you recall previously, okay, what we discussed, it was lambda times here probability of success, and small it was lambda. Okay, so it was lambda time the length of this. Anyway, so let me just write it down because we just discussed this half an hour ago. Okay, it's alpha times this. Okay, so this alpha is playing in our role here, which is a parameter in our distribution here. Okay, gamma distribution. So, and second thing is what? The probability of more than one success, because times is very, very small, more than one success, okay, is very, very small, okay, in such an interval. Such an interval is a small interval which you talked about in one. In such a time interval is negligible, right? Is very, very small. It's negligible. This is also what we defined when we defined Poisson process. And we discussed this when we talked about Poisson process. So negligible, okay. Now another third condition was the probability of success. Okay. This is the independence. Okay, it should be the second one. Anyway, for success in that interval, in an interval, or in the above interval, let's say T2. You can write it open also, doesn't matter, open interval also. This, okay, does not depend on the previous one, okay, or what happened outside of this interval, on what happens, okay, outside this. So this is the three assumptions we had outside the interval. Okay, so lambda here, just to recall, lambda here is something like alpha times t when this t is the time interval. Okay, the length of the time interval. Okay, t is this, the Poisson distribution. Okay, here let's say we talked about that. So here the line length is, let's say delta t. This is the length of the time. So here t and here something t plus delta t. Okay, this is the rate. Okay, so then we need to determine the inter-arrival time, right? The distribution of inter-arrival time or the waiting time. Okay, let y be the, so we wrote it as yk when we talked about geometric and binomial. So same notation I'm using here. Let y be the random variable, okay, random variable corresponding to arrival time, or inter-arrival time, to inter-arrival, or you can say waiting time. Okay, then what happens? What is the cumulative function here? So this we can say it as probability of y less equal to y. Okay, this is what is, and you'll see why I'm finding the cumulative one. 1 minus probability of y bigger than y. This is what is known to us. I want to use that. That's why I'm using. What is that? This is 1 minus what is probability of y bigger than y? So this is the probability of zero success in a time interval, okay, interval of length y. So we already know what happened to that, the probability of this, which is probability, or you can say 0 and then lambda. So lambda here is some alpha times y, because y is the time length. So this is 1 minus, if you recall the definition of Poisson distribution, it is e to the power lambda. So minus lambda to the equal alpha y. Then it is k is equal to 0. So lambda means alpha y here to the power 0 by factorial 0. So which is actually 1 minus e to the power alpha y when alpha y is bigger than 0. So once you get the cumulative one, then how to find the density? So it is, you have to take just the derivative of this. If you just recall our discussion on continuous random variable, then fy, okay, this is ddy of fy. So therefore, this gives f of y is equal to alpha e to the power minus some alpha y is bigger than 0 and 0 otherwise. Okay. And so this is actually the geometric distribution. Okay. Earlier we had 1 by theta in the distribution, right? 1 by theta. So 1 by theta is equal to, 1 by theta is equal to alpha there. 1 by theta equal to alpha there. So which is geometric distribution. Okay, by setting alpha is equal to 1 by theta. Okay. Okay, so now another special case of gamma distribution. This will be a little boring because these are all the definitions only. Okay. Anyway, so this is, I think, fourth one, which is called the chi-square. Okay, and this is very, very useful. You'll see which we'll use this when in terms of sampling theory. Yes.
Sir, I didn't understand the first assumption you made, like alpha, delta, theta. Like, what is alpha there exactly? Like, is alpha lambda?
No, lambda is my alpha times delta. Now I'm just saying alpha is a parameter, let's say, because alpha you want to use. So right, so alpha times delta. So it is, you can assume like it is alpha is the what is called lambda is equal to what? Is time, so k times this thing, right? K times what is the length? Let me just go back. So this k is playing the role of alpha here. I mean, you can write k also, that is not a problem. Anyway, so let me just go back. Lambda, what is that? Lambda, yeah. Lambda is equal to this. What is that?
So n times p you told, wherein n.
Yeah, no, that is corresponding to the binomial. But yeah, I think we have explained this somewhere. Yeah, this lambda times tau here. This lambda times tau. Okay, so lambda times tau, what is happening is, you can say this probability of k success here. Okay, we are talking about the probability of k success. When it is 0, it was 1 minus lambda times tau. Here it is when it is 1, so it is lambda times tau. So you can say like lambda is equal to, now let's say k by tau, or you can say, yeah, so it is something like that. So it is just that, I mean, we are using this parameter because suppose the thing is, we had a parameter alpha. You see, if you just go back, we had a parameter alpha in the gamma distribution, right? This alpha. I have to relate to this alpha, value of alpha, when we are saying that this what is called this exponential, okay, distribution is nothing but kind of gamma distribution. Waiting time distribution is given by this exponential distribution, but exponential distribution follows from this gamma distribution. So what I'm saying is the probability of success, okay, in a small interval time, I'm defining this to be equal to some alpha times delta t. Okay, so my lambda here is alpha times t if t is the length. So alpha is the parameter, some alpha times t. Okay, this alpha parameter I'll be using later on. Okay, so this alpha is I am using here. Alpha is this, and this is this. So when I get this parameter alpha, Now say this alpha is nothing but 1 minus theta. Oh, sorry, 1 by theta in the exponential distribution. So if I alpha, I'm just introducing a notation, which is like, I mean, you can say any notation. I mean, that is not a problem. Alpha, you can write it as anything. Okay, lambda is equal to some alpha times t when t is the time and alpha is some value. Okay, and then what you can say, so alpha is time means, so k success, k success in a time interval. Okay, so let's say this is rate. How to define rate? Okay, so this is the time span, let's say 1 minute. Okay, so per minute or per second, like k accidents per second. So I have to introduce some value because t is this time span is like, let's say t. Okay, like t seconds you have to wait. Okay, or something like 10 milliseconds, 10 nanoseconds, whatever the length is. Okay, what is the measurement you are taking? This gap, time gap is. So then I'm saying this as a rate, alpha, lambda is the rate. So this lambda is equal to some number of times of success. That means some number of arrivals of the accident or some number of occurrence of the same thing in the time interval t, because alpha is per unit time, let's say. So the time is t, so it is alpha times t. So that's the rate. So it is just a parameter, and this alpha is associated with the now this thing, this exponential distribution. In fact, alpha is equal to 1 by theta. Okay, so yeah, that is how it is related. We are say it is like doing the same thing, okay, in a different way and nothing else. I mean, you can assume it like it is mathematical manipulation, that we are playing with different values, and so whatever here is happening. So what happens that if you have two different situations, okay, two different things, and you want to relate both the things, but both the things have different parameters, and the parameters I have to relate it. Okay, so let's say I have one phenomena 1, another is phenomena 2. In phenomena 1 I have different parameters, phenomena 2 are different parameters. Okay, but they are related somehow. Okay, so I have to find out how they are related. Okay, and this is the mechanism how we can find how they are related. So what we can say now, that the weighting distribution, if I just write follows geometric, then this value is alpha. What is that alpha? This alpha is nothing but this one, this alpha, where it defines the rate. Okay, rate of occurrence of this in a time interval t. So lambda is exactly equal to alpha times t. Okay, so that's why alpha is, so this is the same alpha here. So this is how we are relating, that when you say that in arrival interarrival so time, okay, so the interarrival time is the random variable. So I want to find a distribution of that, and now I'm saying that distribution will be exponential. So the parameter in the exponential then has to be related with the Poisson process, because I'm talking about interarrival time, and that is a Poisson process. Okay, so that is coming from the Poisson process. So there is a parameter in the Poisson distribution, and that is called the rate lambda, and rate lambda then has to be linked with the parameter in the exponential distribution. And I'm saying that this is how it is related. So lambda is equal to this alpha by alpha times t, but I cannot just write this alpha to be equal to 1 by theta directly, because then the question, I could have written this 1 by theta, and then I would have obtained this exactly the same as the way we defined this geometric distribution. Then the question will be, okay, why did I assume 1 by theta, not theta? Okay, so if I assume any alpha, so because you see here, this geometric, exponential distribution, here the parameter is theta, but here it is 1 by theta. So I could have also assumed that lambda to be equal to 1 by theta times t. Okay, if I define this, then if I just define lambda to be equal to 1 by theta times t, then I will definitely get the precise exact exponential distribution. Okay, instead of that, I said, okay, it is, let's say, alpha times t, and then you see that if alpha takes the value 1 by theta, this is what exactly the geometric distribution. In fact, for any alpha, it is a geometric. Okay, because when I define this, so not geometric, but the exponential. But when I defined exponential, then I defined it in terms of 1 by theta, because this exponential distribution is obtained from gamma distribution. So it is that I have to link both these things, like the exponential distribution along with, in the light of, let's say, Poisson process or the Poisson distribution. So that is how it is linked. So lambda is equal to, if you just take lambda equal to alpha times t, then how this is linked with this geometric distribution. Did I make any sense?
Yes, sir.
Okay. Okay, now another special case of gamma distribution, which will again so I am using different parameters. I could have used just alpha beta, and I could have written all the distribution. But the problem is, so every distribution in itself has its importance, and there is set of notations which people use. Okay, so I am deriving everything from gamma, but for each distribution I am giving different notation. For example, theta is equal to beta in exponential, because exponential is obtained from gamma setting alpha equal to 1, and beta is a variable there. But I replace this beta by theta. Okay, why I did that? Because most of the books will follow that definition, that this is coming to be 1 by theta. Okay, that's why I did theta. But you can also write 1 by theta is 1 by beta here. Okay, so but yeah, so it is not a problem. So we are redefining this notations, because each particular distribution will have a meaning correspond to some data, and then you can only remember what is the parameter, how it is defined. But if I define everything to be using the same parameter, then you'll be a little bit confused. Okay, what was the alpha for let's say gamma? What was the alpha beta for chi square? Okay, so these functions will be a little bit different, but if I do not use different parameters, okay, if I do not denote the parameters in a different way, then it will be very difficult to distinguish which function for which density function for which distribution. Okay, so that's why I'm doing this. I mean, I'm just replacing the notations. Okay, so this is a little bit tricky and this is a little bit boring. I know that, but still we have to do it. Okay. Anyway, so yeah, so this is a spatial case of gamma distribution. This is a special case of gamma distribution. Okay, by setting alpha. Now alpha and gamma nu by 2, and here I'm fixing beta, constant beta equal to 2. For exponential, I fix alpha equal to 1 and beta remain as it is. Okay, from the gamma. Now again, I am defining a new distribution from gamma itself. So gamma is the uniform, not in the uniform distribution, but uniform is it unifies everything. Okay, all these distributions. So all these distributions, this chi-square, exponential, these are special cases, okay, of the gamma distribution. So alpha, if I write it as nu by 2 and beta equal to 2, then whatever I get, that is what is chi-square. So a random variable, it's x, follows chi-square distribution, or you can say PDF, but you understand. So distribution, if this is the PDF here. So here the parameter is nu. So this is pronounced as the Greek letter nu, nu, nu. Okay. So this nu, if you just put in that, what was that? The beta to the power, I think it was alpha, right? Beta to the power alpha. Yeah. So every time we have to, let me just remember this. What is that? Yeah, beta to the alpha, gamma alpha, x to the power alpha minus 1, e to the power x minus beta. So here beta is equal to 2. So 2 to the power nu by 2, gamma of nu by 2, x to the power nu by 2 minus 1, and e to the power nu by 2 by beta. Beta is I think equal to 4. Yeah. So yeah, I got it. So this will be 1 by 2 to the power alpha, which is nu by 2. Okay, and then it is gamma of alpha, so it is nu by 2. And then I had x to the power minus 1, so it is nu by 2 minus 1, so it is nu minus 2 by 2. And then c to the power, I think it was minus x by beta, so it will be x by 2. Okay, when x is bigger than 0, when x is bigger than 0 and 0 otherwise. And this nu has a name here. So nu is called the degrees of freedom, the number of degrees of freedom. Now, what is that? We'll talk about it, okay? Degrees of, but not now. Degrees of freedom, because this concept of degrees of freedom, okay, arises in many scenarios. Okay, for example, in sampling theory, or here, let's say, descriptive statistics. Okay, so descriptive statistics means when you define mean, median, and kurtosis, whatever, all these measures and variance, all these measures we had. Degrees of freedom also can be considered as a parameter there. Okay, so this has a meaning. Okay, we'll talk about that when we'll do sampling, hopefully. So then we'll talk about this. Otherwise, we'll talk about this later. Okay, we'll see like towards the end, because we have to unify all the concepts, and then we'll define what does it mean when you say it's number of degrees of freedom. I mean, intuitively it means, let's say if I ask you a simple question, okay, what is the population of India? Okay, okay, what you can say, okay, we had a consensus maybe 2011, okay, and then we had some population, but after that it changed, right? Now suppose I ask you, make a guess. I call certain experts, okay, who kind of like people like who do that, okay. I ask them to make a guess. They'll make a guess, but I can only ask maybe finite number of people. There are only finite number of experts, okay. So I'll get different values. Like somebody will say, okay, it's let's say not 1 crore, but it is let's say 150, okay, in terms of crores, so in terms of billions. And then somebody will say, no, it could be 140. Okay, somebody may say 147, okay, and so on. Okay, maybe I ask this to 5 people. Okay, so let's somebody say 145, and somebody says let's say 160. Crores of people in India, suppose, but I have no idea exactly about what is the population. So this is like a sample. Okay, this is a sample value. It could be this, it could be this. This is how it goes on. Like when you do a sampling, okay, you only ask a few people, okay, and they give you some answer, okay, and that's how. From there, you have to make a judgment. Okay. So now the question is, now suppose I have to find out what is exact the number. So once these values are given, from here I can have a sample mean. So I can sample mean, these are all the sample values of the same thing, which is let's say the population. Okay. Then we can calculate, we have these values, then we can calculate the mean, we can calculate the variance, all these parameters. Okay. We can compute based on these 5 values. Okay. But the question is, how do I know the exact population? What should be my best estimate? Okay. So best estimate means what is the best estimate for the mean? Here, this is a sample mean. This is not the exact mean. Sample means this is the average or the expected value of the sample values. But I want to find out the exact mean. So how do I estimate that? So when we will talk about estimation, then also you have to talk about freedom, degrees of freedom. Now, degrees of freedom is actually, I mean, not actually, but let's say upper, maybe I would say approximately. Okay, it means the number of information. Information is a big word, but let me say in a generic sense. Okay, number of queries. Let's say I have to ask. Okay, so that I'll get a better estimation for the entire population. So there is also a parameter which is involved with the sampling. Okay, this is the number of queries. Let's say I have to ask minimum number of queries. Let's say I have to ask, okay, to predict, let's say the exact, or to determine, let's say the exact number of population, or very close to the exact number of population. So then that is also a parameter which is actually degrees of freedom. Okay, so we'll discuss this degrees of freedom, but not now. Okay, not now. Okay. So we'll talk about that later, because we have to discuss also chi-square test. Okay, this chi-square test is very, very important. Okay, so we'll talk about that. So when we talk about chi-square test, there is something called chi-square testing, hypothesis testing. Okay, so we'll talk about chi-square test, and then this will play a big role. So that time we'll discuss what is the number of degrees of freedom. Okay, but this is how it is called. This new is called degrees of freedom. And now suppose I want to compute all the means and variance, okay, mean and variance of each of this distribution, let's say the chi-square, or the exponential, and the gamma. So it is enough if I can calculate the mean and variance of gamma. From that, I can calculate mean and variance of exponential, as well as I can compute the mean and variance of exponential and that. So yeah, so we'll just compute the mean and variance of gamma, and from there it will follow. Okay, maybe we can do it next day. Okay, we're running out of time, and this is where we end here. I think the next class will be tomorrow. There's no class. Next week there is no class. So next class will be Monday, March 8th. Okay, I think that's a Women's Day or something. Okay, so Mother's Day or something. I don't remember anyway. So yeah, so we'll meet next day, which is 8th of March. Okay, long time. So if you have any question regarding today's class, you can ask me, and then possibly can discuss it. Yeah.
Will the best